So let me start by thanking the organizers to give me an opportunity to speak here. Honestly, it has been a while, at least a couple of years I have worked on edge state, but once this invitation came, I really thought I should get back at it, which was good. And then, so what I will do is, I'll try to summarize results which we had from last 10 to 14 years, I would say, and which was during my postdoc period, mostly when I was here in IISc, in Bangalore, and tell you what new we are trying to do right now based on those results. Okay, so the main motto would be to convince you that junctions of chiral Luttinger liquids are really interesting objects to look at. They really host interesting physics. So that's what I'll try to motivate. So I'll start by really looking at something very simple, which is the nu equals to 1 edge state, which is believed, assuming that there is no edge reconstruction. I'll assume that that's just a simple Fermi liquid. So that's the simplest thing you can think of, electrons running only in one directions. And if you try to make some circuits out of it, you will try to first try to make a point contact or multiple point contacts where a couple of edge states come together, scatter with each other. And the question I would like to ask is there a connection between the dissipation which such a circuit holds, so the amount of dissipation which happens due to tunneling between these edges. So essentially when you bias these edges, you impose an equilibrium distribution on these incoming edges, and then the tunnel between each other and a non-equilibrium distribution is generated in the outgoing edges, and once these states equilibrate, they're going to dissipate. So essentially, I would define dissipation in the sense of like you define 4-terminal resistance, where you don't take the dissipation happening at the contacts, it's only in the sense of what is happening right at the scattering center. And I'll try to make a connection, if it is possible, I'll try to make a connection with the noise generated in the circuit as the tunneling happens, right? So it should be a very simple-minded thing. It's a free electron picture, and asking a very simple question that if you have, so I'll skip, maybe this is not needed. We have enough introduction to quantum Hall edges. So what you have is a simplest geometry is a 2-terminal geometry. You think of a one-dimensional wire where there's a small scatterer sitting in the middle. You impose a chemical potential mu1 to the left. It's a zero temperature picture. To the right, mu2, where mu1 is not equal to mu2. Rather, mu1 is greater than mu2. And then if you switch on large magnetic fields, you break time reversal symmetry. So essentially what you expect is initially right movers and left movers, which are time reverse partner, which are sitting on top of each other. They should separate out physically, and the picture should start looking like this. Now the advantage is that you can address these outgoing edges individually and experimentally really address them and ask what is going on there, which is not possible in this geometry. So now if current is coming in, so you inject current from here, and some tunneling is happening, some reflected current is going this way, some transmitted current is going that way. That generates a non-equilibrium distribution, and what you can ask is how much, if you equilibrate that distribution into a zero temperature distribution, I think that's the maximum amount of work you can take out of the system, right? Once it settles down to a zero temperature distribution, there is no more work you can take out of it. So I'll define that as the maximum amount of dissipation you can have, and the connection I would like to make is between the maximum amount of dissipation this circuit allows with the maximum amount of noise which it generates, which is basically if you measure the autocorrelated noise in this terminal and that terminal, you sum that up. So if you have an n-terminal geometry, what one has in mind is that take all the outgoing channels, sum up the autocorrelated noise, and see if there's a correlation between the sum of the autocorrelated noise and sum of the total four-terminal dissipation as I defined it. The dissipation which is not happening at the contact, but purely due to equilibration of non-equilibrium distribution generated due to tunneling. Very simple picture. One is asking, is there a connection? You would expect some connection because you can't really dissipate unless you have fluctuations. So noise is nothing but standard deviation of current. So essentially what you're saying is current is fluctuation, there's occupancy fluctuation, and you naturally expect there should be some simple connection, the simplest possible scenario, between the total dissipation and total noise. So that's what I will try to first address, that is there a connection? And if there is one, how can you quantify it? And we'll see on the way as we define dissipation, as we try to quantify dissipation, this 4-terminal way of quantifying dissipation, this will lead to a natural way of going into more complicated physics from just the nu equals to 1 physics, where we'll start seeing structures of fixed points, non-trivial fixed points of such theories when there are interacting edges coming together, just by looking at dissipation. And then I will try to go to low energy description and bosonization and so on, and justify how that can be obtained from more concrete grounds. Okay, so the picture is this, as I said. So impose these two chemical potentials on the two sides. As you transmit, you get a two-step function, distribution function. So this is the two-step distribution function on this side. So it's kind of filled here within the bias window up to with the probability t, and beyond that it's filled with probability 1. And similarly here it's a two-step function with this being r. Now you can just ask this question that if I equilibrate this object, if I take this two-step function and kind of reduce it, keeping the particle number same, if I reduce it to an equilibrium or rather zero temperature distribution, how much energy do I relax? So that's the maximum amount of energy you can take out of the system, because it's a Fermi system, you can't take out anything more. So if you just calculate this, so before I go, so maybe I'll. So when you try to do that, so this chemical potential, which is an emergent chemical potential here, which is T times mu1 minus mu2, this is something which you can measure using a 4-terminal measurement, which is well known. If you introduce a voltage probe, which the 6-terminal measurement definitely has the ability to kind of ask that what is the local chemical potential on this edge, that is how we actually measure the longitudinal and the transverse voltage. So we can measure this quantity here, which is the equilibrated chemical potential. So if we can do that, then we can ask this question, what is the dissipation in each branch? So essentially that's a simple calculation. It's energy times the distribution functions times the transmission function as a function of energy. You integrate that, and if you do that, assuming that you are at small biases and T is independent of energy, you get a simple expression for the transmitted power, which is something like this, E squared over H times T times 1 minus T times VL minus VR whole square, okay? And it turns out for a two-terminal geometry, which is the simplest possible case, the dissipated power in this, though the distribution functions are different, but if you look at the dissipated power in this branch and that branch, they're exactly the same. So that's of course not a generic feature. As you go to more complicated junctions, this will go away and something else will take over. But that's the simplest expression. But I mean, if you stare at this expression, it immediately kind of also triggers a thought in your head that I know that the shot noise also looks like this, T times 1 minus T, right? It's exactly the expression of shot noise. If you look at this, it's very similar to that. So if you so it has, at least in the two-terminal context, it has a similar structure. So the noise and the total power dissipation goes pretty much, as far as the S matrix dependence is concerned, is very similar. So you can you can kind of make this more concrete. What you can say is that let's take the input. You can write the input power. If you have n-terminal geometry, you can write the input power as an inner product of two vectors, where this vector V, essentially I is for incoming channels and V is a vector, which is essentially inputs, which are the input voltages V1, V2, Vn imposed on each of the incoming channel. So you can efficiently write the power, input power as the conductance by 2, V dagger V, right? And similarly, if the equilibrated voltage on the outgoing branch is V out, a vector V out, then you can write the output power. So essentially, if you take the difference between the two, that gives you the dissipation. So you can write it in an efficient way. So you can essentially define this object here, where you can convert the voltage. So this is a matrix M which connects the outgoing voltages to the incoming voltages. Essentially, you can think of it as some sort of a current splitting matrix. So you have a current splitting matrix, tells you how the incoming current splits into the outgoing current. And if you know that matrix, you can write the power dissipation, the 4-terminal power dissipation, as G over 2 V vectored input times identity minus M dagger M times V input. Okay, so this is a nice way of putting it, and we'll see that why this can be quite powerful as even we go to interacting cases. Because you see that here, once you start talking about currents, it really doesn't tell you the current is carried by a fractional quantum Hall edge or an integer quantum Hall edge. It really doesn't matter. If it is a current splitting matrix, the argument stays put. So what are the properties of this M matrix, the current splitting matrix? So what you have to ensure is that as you increase the voltage on each of the branch, if I globally increase all the voltages, nothing should change. Essentially, the net current on each of the branches should not change. So that imposes that the rows should add up to 1. The column should add up to 1 because of charge conservation. And of course, we should not dissipate more power than what you put in. That ensures that the eigenvalues are bounded between 0 and 1. So that is the property. So in principle, if I forget about the details of how I came here, if I have a bunch of incoming edge state and incoming outgoing edge states, I can write such an expression of power dissipation. And this M-Dagger M matrix should have this property irrespective of it is described by a Fermi liquid theory or some Luttinger liquid theory or anything else. This has to be true. So how do you find out what is the maximum power dissipation and what is the minimum? Minimum is simple. It has to be 0. If you impose the same voltages on each branch, then you will get 0 dissipation. But how do you find out what is maximum? So there is an easy way of looking for that. You just look for eigenvalues of this. So if you prepare an eigenstate of this M-Dagger M operator such that this has 0 eigenvalue, then you know that whatever power you put in, that fully dissipated. The simple way of doing it is just look for eigenvalues and eigenvectors of this operator. So in an n-terminal geometry, that gives you an efficient way of identifying what should be the voltage configuration, given an S matrix, what should be the voltage configuration so that you have maximum power dissipation. And if you have the right S matrix, then you can have even the fully dissipative case, where whatever power is input is entirely dissipated. Right? So yeah, absolutely. Oh yeah, it's a real matrix, so it doesn't matter. Yeah, absolutely. It's transpose only. Yeah. So for example, if I have a S matrix like this, the current splitting matrix is nothing but a matrix which corresponds to mod squaring all these elements that will essentially tell me how the current is splitting at the junction. And then if you go ahead, you can calculate these eigenvalues of this M matrix, and that will tell you what kind of voltage configurations will give you maximum dissipation. Here you see that I don't really see an eigenvalue 0 here. So it's not ensured that given an arbitrary scattering matrix here, you'll really have a 0 eigenvalue. So if you have the right kind of scattering matrix or current splitting matrix, then you can have a possibility of choosing voltages so that you have maximum dissipation. It's not ensured a priori. So now what can you learn from it? There's something very beautiful which comes out of this simple thing is that if you look at, so we have this condition that, the rows have to add up to 1, the columns have to add up to 1, and if you do not want dissipation, this has to be orthogonal, right? That's a simple argument. M has to be an orthogonal matrix. If you impose all 3 conditions, and then you do not care if really this kind of theory refers to a free fermion theory or an interacting theory, this is the general argument, then you can ask this question, for a 2-terminal case, what are the all possible M's I can have? So it turns out that this is a very simple thing to work out, that if you look for orthogonal matrices whose rows add up to 1, whose columns add up to 1, and so yeah.
I didn't catch why the requirement that M was orthogonal.
No, I mean, I want no dissipation. So I want just identity minus identity. I want identity minus identity. M-Dagger M is identity.
Oh, I see.
Yeah, dissipationless. I'm asking this general question. What should M look like so that it's dissipationless? So, so then it gives rise to this simple thing which should be 0 once it's either perfectly reflecting or perfectly transmitting. This really goes back to this Luttinger liquid physics where you know a single impurity problem only has 2 fixed points, right? So fixed points are non-dissipative. They have to satisfy this condition no matter what the details are. And it's really connected to that. It essentially ensures that there are only 2 fixed points, either it's perfectly reflecting or perfectly transmitting. This description fits in. I'll try to convince you more on the way through the field theory, but you don't need any field theory. This argument already gives you these 2 fixed points. I'll show you that there are more non-trivial possibilities possible, provided you have junctions between Luttinger liquids with different Luttinger parameter, inhomogeneous Luttinger liquid. But even then, you'll have new matrices coming in, but they will be non-dissipative, and they will actually give you the fixed points of the theory. So that has been explored by, I think there's something called a Halperin Transformer. I don't know if you have looked at it. They proposed a transformer based on exactly this physics, that what kind of fixed points will you get if you have 2 different filling fractions being tunnel coupled at a point at the strong coupling limit. Okay, now if you take the 3x3 case, so essentially what the 2x2 case is telling me is that if I just impose this condition that you should not have any dissipation, then there are actually 2 fixed points in the theory. But this argument is of course at the level of expectation values. So what I'm looking at is average currents, and I'm making some statements. I'll go ahead and write some field theory and try to convince you. The same thing comes out of writing operator expressions, where this expectation value will of course satisfy that. Because this is an argument at the level of average currents and dissipation. Okay, so now this tells you that if you look at the 3x3 case and start asking this question, then how can we write matrices whose sum of rows and columns add up to 1, and at the same time they're orthogonal? Okay, so you can write this one parameter family. There are two. So this is, you see that this is a family in which is a Z3 symmetric in the index of the 3 wires. So if you have the first edge, second edge, third edge level at 1 to 3, as 1 goes to 2, 2 goes to 3, this M matrix remains invariant. It's like symmetric, Z3 symmetric matrix. It can be parameterized like that. And there are two such classes. One respects time reversal symmetry. The other one doesn't respect time reversal symmetry. And this actually, if you plug them in, you see that they are dissipationless. And they do describe, so I'll later on show you, they do describe fixed points of the theory. So without getting into any bosonization, any such thing, no field theory, simply starting from this argument of zero dissipation, and imposing this condition that you have quantum Hall edges, which has, the voltage is related to the current by the Hall relation, you can completely come to this description where you get the fixed point boundary conditions. That's really beautiful. You don't need to get into any field theory argument here. But I'll, of course, show that this is correct.
Are you able to cover the maybe in the formulas from this set of assumptions?
But Yuval, the question is, okay, so this is a fixed point description, right? On top of it, you're going to switch on perturbations and then ask this question that what kind of transport is happening around it. This is really at the fixed point.
No, but I thought that you started with a general formalism, which was not necessarily fixed point, only assumption of no dissipation.
Yeah.
But including interactions.
Including interaction. So I'm not referring to any. Yeah. Okay, good. So let me answer you this way. Right now, I'm making an argument which is at the level of average currents. I'll show you that this is consistent with the fixed count description, which I've not done. It's a claim. I'll show you this happens.
So it's consistent with what?
A description of a fixed point. So these matrices will exactly appear as the boundary condition which stitches your field coming at a junction, really at the level of fields.
But at the moment, you don't know whether...
At the moment, yeah. Yes. I'll show you that this is really consistent. Yeah.
Fixed points are non-dissipative?
I really don't know. There are possibilities of fixed points which can be dissipative, but right now I'm looking at all possible fixed points which are non-dissipative. We can have fixed points which can be dissipative, surely. Yeah. Okay, so the simple ones, so if you look at this matrix, the simple ones are those which can be realized both with a free fermion theory and a non-free fermion theory. So free fermion theory will be, so how do I know that this is really coming from a free fermion theory? You ask this question that I have given you a current splitting matrix. Can I motivate this current splitting matrix by mod squaring a unitary matrix, which is an S matrix? If I can do this, I know that this description fits into a free fermion theory. If I cannot do this, I know that this is coming from an interacting theory. That's the simple prescription. So if you have matrices only with zeros and ones, so this is a matrix which is completely, at the junction you have perfect reflection. Everything is reflecting back. There's no talking between 1, 2, and 3. That is this one. It's trivial. Of course, both for the interacting and the free case, you get the same answer. Then you have these guys, which are chiral fixed points, where there's a perfect transmission from 1 to 2, 2 to 3, 3 to 1, and this is the time reverse partner of that. And they can also be both interacting and free and described by the same current splitting matrix. It will be more tricky once you have things which are not just zeros and ones, and then you can clearly distinguish them. For example, if I look at this parametrization, I can assure you that you won't find a unitary scattering matrix whose mod square elements will fit into this kind of a matrix, this kind of current splitting matrix. So essentially for each theta, you have something which is, this is definitely describing a non-Fermi liquid theory. So now the interesting question. So can you have a current splitting matrix with a negative element? That will be really interesting because if you have negative elements in the current splitting matrix, it is analogous to having Andree reflection, some sort of an Andree reflection. Can you have that? Which essentially saying, can you have non-trivial fixed points which have this property that current is coming in and holes are bouncing off on the other side, right? So this is very well known, and this is there in a two-terminal geometry. So I'll try to convince you of that. That's exactly Chklovskii-Halperin transistor, and then many others have looked at it. So what one is saying is that, so with the free fermion theory, of course, it's not possible to have an M matrix with negative signs in its elements. That's not possible. So if you have junctions between FQHE, fractional quantum Hall edges with different filling fraction, not with same, then you can have fixed points where indeed this can happen. And that's not surprising. And I'll argue why. It's exactly like having Andree reflection. So when you have a superconductor on one side and normal metal on the other side, you think of sending in an excited electron that pairs up with another electron and goes into the superconductor, a whole bounce off, right? Now think of a junction between a nu equals to 1 and a nu equals to 1/3 state. If you have a strong coupling fixed point between the two, you can think of a situation where a 1/3 quasi-particle, excited quasi-particle is coming in, it wants to go into the nu equals to 1 state. Of course, it cannot go in, so it will pair up with some, two more quasi-particles, and two quasi-holes will bounce off on the other side. That's exactly the fixed point description which allows you for having negative elements in this current splitting matrix. They're very interesting, actually. So this is like the superconductivity will, of course, do that, but mismatch of filling fractions can also give you similar physics. You can get negative elements. As I said, they represent analog of the Andree reflection process. And they can be really interesting. So what I'll show you later on is that you can get really interesting physics out of these negative elements, something which you do not see usually in Luttinger liquids. So let me kind of jump ahead and just tell you that, for example, in Luttinger liquids, we know that it's a non-Fermi liquid theory and electrons have no place, which basically means that zero energy, if I try to introduce an electron at the position x, I'll really see an orthogonality catastrophe. I'll see that it says all the states which are there are completely orthogonal to the state which I'm trying to create, which means I cannot inject that electron. What I will try to convince you is that you can have such negative elements, such as negative elements in the current splitting matrix, which describes certain fixed points, interesting fixed points of the theory, where this is completely reversed. You actually welcome the electron to come in. Right? That's one of the unique things which is there in this physics, and this is what I'm trying to tell you, that you can get new physics out of it when you look at such processes. Yeah? No, you cannot have it for free electron. That's the whole point. You cannot have it. You can only have it for interacting. No free electron theory can give you that. Unless you, of course, put superconductors in. You can't have holes bouncing off. Right. Okay, so this goes back to Venn. Now, so the first paper which I can think of where this is already discussed is 1994 by Venn, where he writes down exactly a current splitting matrix, and he defines the current this way, and then he's discussing a situation where there's a mismatch of filling fraction, introduce a dissipation parameter, but if you put the dissipation parameter to 1, which is the limit when it's dissipationless, then you see that you get a matrix which splits the current in such a situation. And if you look at this one, it's exactly like if you put t equals to 1, this is nu1 minus nu2. This is nu2 minus nu1. So essentially, depending on the filling fraction and the order of the filling fraction, nu1 greater than nu2 or nu2 greater than nu1, you definitely have negative elements in the current splitting matrix. It's there. But you need a mismatch of filling fractions for that. Based on this, actually, so as I argued that you can think of between nu equals to 1 and nu equals to 1/3, if you have an excited quasi-particle coming in, it has to pair up with other two quasi-particles before it can go into nu equals to 1, and two holes will bounce off here, quasi-holes. And that's exactly what you see coming out of this splitting matrix. The element which goes negative, the current which goes negative, really appears on the 1/3 edge on this side, on the backscattered side. This is really consistent. If you think of such a picture, it fits in. Okay? Now, based on this, Halperin in 1998 really proposed this transformer. So it's a very interesting design where he took this fixed point. It didn't really write in this language, but essentially they had this fixed point. They had a long edge with some inter-edge interactions and so on. But finally, they could devise this one where there is adiabatic contact between nu equals to 1 and nu equals to 1/3 and 2 points. And if you impose a voltage between 1 and 2, what you can show is that that voltage difference will be amplified 3 times with nu equals to 1/3 edge between 3 and 4. So that was the transformer. This exactly uses this physics. And later on, Slender, Shimon, and Fritkin indeed called it an Andree reflection process, where they exactly looked at this. And it connects, as I said, that it exactly connects to this physics of inhomogeneous Luttinger liquid, where you think of two quantum wires which are connected at a point with Luttinger parameter K1 and Luttinger parameter K2, and we assume that there's a smooth junction here where there is no back reflections. It's essentially a strong coupling fixed point. So this thing here, so this strong coupling fixed point between nu equals to 1 and nu equals to 1/3 is completely same as this one, as we know that we can just map the Luttinger Hamiltonian to a quantum Hall edge Hamiltonian with Luttinger parameter being replaced by filling fraction. So it just maps onto one another. Okay, so that's that. But coming back, so what I tried convincing you here is that the current splitting matrix is really very interesting object. Without getting into really the microscopic details of the theory, you can predict a lot just using this, and measuring that in an experiment is hence very interesting. It could be very interesting and really come to conclusions which are non-trivial. Now, short noise, I think short noise has been discussed in details in this conference, in many talks, even the previous talk and Bert's talk, there was a lot of discussion on short noise. So what you can do with short noise is you can use it as a thermometer. It's a very sensitive thermometer. If you go down to temperatures where the electron gas really decouples from the lattice, you can use that for really measuring the temperature of the electron gas itself. Then it can be used for determining quasi-particle charge in under appropriate circumstances. And then, of course, you can also use it if you look at cross-correlated noise. You can also use it using situations like HBT effect. You can actually address quasi-particle statistics. So it's very useful, and what I'm trying to do, I'm not going to do any of this. What I'm trying to convince you, as I started, I told you that what I'm going to do is trying to get at a relation where I'm looking at the total noise generated in the circuit, summing it up, and looking at the total dissipation in the circuit, and trying to see if there's a linear relation between the two. It's some sort of an out of equilibrium fluctuation dissipation kind of relation. So as I said, that if you look at the power, if you look at the autocorrelated noise, it goes like this. It's T times 1 minus T V1 minus V2 E cubed by 3. But the power dissipation goes like that. It's T times 1 minus T V1 minus V2 whole squared is squared over H. So naturally that if you just take the ratio, you see that there's a nice linear relation. One can write a nice linear relation between them, which is independent of the scattering matrix, which stays between them. If you just take the ratio, so T times 1 minus T cancels out. And the question would be that if I try to generalize this to not 2-terminal, but 3-terminal, n-terminal geometry, just such a ratio holds. So what one is asking is, does the correspondence between noise and dissipation extends to n-terminal case? Does the maximum dissipation correspond to maximum noise? So what is the correct thing to look at? Maybe the correct thing to look at is the sum of autocorrelated noise should be related to sum of dissipation in outgoing channels. So we try to do that. We write down the expressions in terms of current splitting matrix now for the noise and dissipation, and we see that at least if you look at the components which correspond to different voltage differences, they are actually identical. So one thing which you immediately come at is that if you really put only one voltage, impose one voltage in one of the incoming edge, and put all the other voltages to 0, and then compare this quantity, this ratio is a nice ratio. You can say that power dissipation, the total power dissipation, is equal to 1/4 times E times S autocorrelated times the voltage bias. So there is a nice relation which you can write. And what is this useful for? So if you could measure the noise, of course, it's regularly measured. The power dissipation can be measured in the sense that you can, of course, put voltage probes on each of them and read off the equilibrated voltage. So you can try to make a connection between the two. And if you could confirm this relation, it will tell you, so nu equals to 1 edge is really, when there's always a question that is it a reconstructed edge? If you try to build interferometers, and I've heard 100 times from Murthy that when he tries to build interferometers out of nu equals to 1 edge, there's a lot of confusing results which comes out. It always, it can give anomalous result. So this will at least confirm that nu equals to 1 edge is a Fermi liquid edge or not. If you could confirm this relation, this ratio, then definitely it will mean that the Fermi liquid physics is at work. So now you can ask this question that if all the voltages difference are different, then will such a relation hold? And it does hold if you impose cyclic symmetry. So again, Z2 symmetry, Z3 symmetry for its 3-terminal junction, Z4 symmetry for a 4-terminal junction, then you see that actually you can bunch them up in a nice way. And again, the ratio is something which depends on the details of the voltages, but what drops out from it is really the details of the scattering matrix. So essentially the ratio is independent. Once you impose this symmetry, the ratio is independent of the scattering matrix. It does not matter how so essentially the scattering matrix is, you can think that is the resistor network, right? So because each transmission is telling you what is the resistance at the junction between different wires, and that object drops out. What remains is a function of voltages and the total dissipation. So that's nice, it's universal in this sense. Okay, so let me move ahead. Now, how much time do I have? 15 minutes? Okay, so coming back to interacting edges, and as I promised that looking at the dissipation matrix or this current splitting matrix, we could predict fixed points of the theory. So one has to, of course, look at it more carefully and see that if really those matrices represent fixed points of the theory, and I'm going to do that. This is a quick, so I think there are enough introduction to quantum Hall edges, so I'll quickly skip it. So essentially, on the edge, so maybe I just make a few comments here. So if you want to construct, so I'm going to use bosonization for describing the edges. So this was first done by, for interacting edges, it was done by Wen in 1992, and he assumed a hydrodynamic mode which exists on the boundary of the quantum Hall edge, and he claimed that it can be described by such an Hamiltonian where the dou x phi is nothing but the density on the edge, and which is written here. And these fields, and these are bosonic fields, and these bosonic fields have these commutation relations given here. And the good thing about them is that so you can construct electron operators, all quasi-particle operators using them. So e to the power I phi by nu essentially is a construction of the right electron operator, while yet there should be a Klein factor here also for the quasi-particle. So e to the power I phi would be a construction of a quasi-particle operator. Essentially, if you look at the commutation relation between the density on the edge and this creation operator, you see that it creates the right puncture at the position x, right? So it tells you that it really has the right operator which creates the right density puncture there. And it also has fractional statistics, as you can see that if you exchange these two objects, you get this phase factor, which is neither zero, so it's neither zero nor -1, it is something in between, and it's given by pi nu. So that's the fractional statistics, and I won't get into the details of how one can look at it from the perspective of bulk, but that's what it is. So I'm going to use these bosonic fields now to describe the edge and try to find out what kind of fixed points can you think of when you think of junctions of these edges. So let's start with the simplest case where you can write a field splitting matrix where these are the incoming fields. So this is a quantum Hall edge, this is another quantum Hall edge, something I'm not saying what is going on here. I'm going to find out by applying appropriate boundary conditions. So there are 4 points here. So this edge ends here, then this edge starts here, and this edge ends here, and that edge starts here. So whatever comes into the junction, I call incoming. Whatever goes out, I call it outcoming. And then what you can write is a matrix which connects these two vectors where these are these incoming fields and outgoing fields. And then you can ask, what is a good M? So now it is not a current splitting operator, it's essentially a field splitting operator. It's really an operator statement. And you can ask this question, what is a good M? So the conditions which you need to put on good M is that all elements of S has to be real, of course. Columns should add up to unity. This is current conservation. And conservation of the energy momentum tensor. So if you apply the energy momentum tensor to be conserved across the junction, then you get this condition that this so squares of these matrices, so this Mij should add up to 1. Okay? So these are the 3 conditions, right? So this actually, so once you put this condition, this essentially fixes the whole thing that tells you that it is at least describing a non-dissipative fixed point of the theory. So now if you put this condition and you apply it, you immediately see that if I write such a matrix, 2 cross 2 matrix, which is describing this field splitting matrix, and I apply this condition, then this is the condition imposed on it, and it tells you there are only 2 possibilities, p equals to 0 or p equals to 1. So that comes back to what we got back from dissipation. So when I first arrived at this 0 and 1 condition, this was purely on arguments of non-dissipative, a situation where there are incoming currents, outgoing currents, and what you wanted is no dissipation. And here we are really coming from the bosonic fields and asking what should be the condition where the energy momentum tensor is kind of conserved at the junction. And you actually come at the same condition that there can be only 2 fixed points in the theory. Either you're perfectly reflecting or perfectly transmitting. So it seems to be consistent. Now you go ahead and you can do this for 3 cross 3 case, and again you play the same game, and you end up getting these matrices which I showed you for the case of dissipation, and they exactly fit in here. So exactly the same set of matrix you end up getting as you impose this conservation of energy momentum tensor at the junction. So it's telling you that from the dissipation argument itself, I could have predicted this set of fixed points. So Yuval, this I hope answers your question, right? So this is really coming from the fields now. It's not really an approximate, it's not a statement at the level of expectation value. So there the statement was I wrote the current operator, then I took the expectation value, and at the level of expectation value, there was connection between the incoming currents and the outgoing currents. Here, this is an operator statement. So now you can go ahead and calculate correlation functions, etc. from here. And yeah. So now for these cases also, you notice that, so in the previous case where I showed you that Halperin and others, what they looked at is a 2x2 case where there was a mismatch of filling fraction. The interesting point is once you promote yourself to junctions of 3 quantum Hall edges, with a uniform filling fraction, you start getting fixed points which already had this Andree reflection kind of character. So essentially, if you can think of it this way, that if you send in current in one of the incoming edges, what reflects back is a hole with 1/3 charge, and what transmits is excess charge of 2/3 and 2/3 on the other 2 edges. Right? So this is what this fixed point describes. And this fixed point really, so what you started looking at is so one thing which you could look at for this kind of fixed point is the tunneling density of states. So you can ask this question that because there is an Andree kind of process, is it possible that for a Luttinger liquid, actually if you try to inject an electron into the state, is actually welcome. It's not suppressed, rather than it's enhanced. So you can easily plug this in. So tunneling density of states, I will talk about, very quickly, I'll talk about 2 cases, 2 possible cases. So you can think of boundary conditions where, so the kind of boundary conditions I showed you is essentially boundary conditions where charge is conserved, right? So that's what I said, there's a charge conserving boundary condition. But you can also start thinking of more generalized boundary condition where actually the incoming edges are connected to the outgoing edges via some superconducting boundary condition. Essentially, the idea is that you have kind of number of incoming edges coming in, which can be even fractional quantum Hall edges, and fractional quantum edges going out, and in between there's a superconducting island which can absorb 2 units of charge. Now you can imagine that, of course, if it is n equals to 1 state, then there's only way it can donate 2 units of charge into the superconductor is pairing up 2 electrons. But if you have fractional quantum Hall edges, there are lots of possibilities of really taking different kind of fractional charges between different edges and making 2 units of charge. So what you look at is essentially boundary conditions which allow for incoming currents to violate 2 units of charge as it goes out. And what you can show is that these boundary conditions, actually the charge conserving boundary condition and charge violating boundary conditions, are exactly dual of each other. In a sense, there is a scaling, the scaling laws exactly go from k to 1/k. If the Luttinger parameter is the parameter which defines these boundary conditions, then if you go from k to 1/k, you get all the relevant power laws of all kinds of perturbations which can switch on around this fixed points which is described by this theory. So starting point, so what you are going to look at now is tunneling density of states. All you're asking is a simple question that if I have a many-body state and I'm trying to inject 1 electron into it, which is like saying that I'm going to create an electron by this creation operator acting on the ground state of that system, then you ask that what is the overlap of this state with 1 more electron with all possible many-body excited state of that system with that particle number. So if this overlap between these two states goes to 0, that is when you say that there's a complete suppression of tunneling density of states. If this overlap tries to diverge in certain cases, then you say there is an enhancement. So the usual physics is that for Luttinger liquids, because electron is not a good quasi-particle, this overlap will simply go to 0 at 0 energy. If something else happens, that is what is interesting. So if you just calculate this correlation function, you can just write the rho of E as e to the power delta minus 1, where delta is something which depends on the filling fraction, the Luttinger parameters, interaction, etc., etc. So essentially what one is looking for is a possibility where delta can be less than 1, which corresponds to enhancement. So what you are expecting is a 0 bias anomaly. Either, so if you're thinking of an STM tip which is trying to inject electron into this system, then at 0 bias, either you have a peak or a dip. So if you have suppression, you will see a dip, and if you have enhancement, you'll see a peak, right? And that's what one is looking for. So it turns out that if you take two quantum Hall edges coming in, and you can switch on interactions, you can switch on all possible filling fractions which you desire. If there are only 2 bosonic edges, no matter what you do, what details you put in, the physics remains that it's always suppressed. There's no way to get out of it. So we have tried all possibilities, and it is always suppressed, no matter what you do. So really the 3-edge construction, that is where it has an edge, if you wish, that it really can turn this around, and it can give rise to an enhancement. So that's the interesting physics. So if you look at the standard, so I'm left with 5 minutes, okay. So if you look at the standard results from tunneling density of states, if you have a long Luttinger liquid and you're trying to inject something in the middle, then delta looks like something like this. in the bulk, which basically means that no matter, so this is the Luttinger parameter, which is greater than 1 for attractive electrons and less than 1 for repulsive electrons. And no matter you have attractive or repulsive electrons, this remains greater than 1, which means you have suppression. So you really have orthogonality catastrophe at work. You really have this orthogonality at work, no matter it's repulsive or attractive. Now, if you look at the boundary, which is a half-wire, think of a situation where you really have half a Luttinger liquid, and you're trying to tunnel in something here, then the physics is a little different. So the power law turns out to be 1 over G. So it is suppressed definitely for K less than 1, which is repulsive electron, but it can be enhanced if you have attractive electrons, right? So
the boundary is a wall or
it's a wall. It's a wall. It's a dead end. So I'm looking at the vicinity of the boundary.
but according to this picture, the boundary is a direct source.
No. This is this result, Yuval, and this picture is not there, which I drew here. So this is for the boundary. This is for the bulk. When I say boundary, it's a half-wire. I'm sorry. No. I'm sorry. This is the boundary. What I mean by the boundary is the half-wire. It's a half Luttinger liquid. Not clear? I'm asking two questions. One is there's an infinitely long Luttinger liquid, and you're trying to tunnel in something here, and you have a half Luttinger liquid. You're trying to tunnel in something at the boundary. So these two scale like this. So it tells you that something interesting can happen in principle if you have attractive electrons. So one can ask this question that if I have such a geometry and I really switch on superconducting boundary conditions, for repulsive electron, will that give me an enhancement of tunneling density of state? This indeed works out fine. I mean, this is, if I have time, I'll show you. So the next step is that we really work this out for a junction of 3 wires, and it turns out that if you really work this out, you get a delta which looks like this, where what we have done is we have done a perturbative expansion of delta in the Luttinger parameter G minus 1. So I'm assuming that I'm really close to being a free fermion. Either I can be slightly repulsive or slightly attractive, depending on G is less than 1 or greater than 1. We do a perturbative expansion, we write down the delta, and what you have is delta equals to 1 minus A times G minus 1, where if I consider this fixed point as the description of the theory, where A's are these diagonal elements, then what you have for A is minus 1/3, so you can naturally see that this will be less than 1. So essentially it's telling you for weakly interacting electrons, for a junction which is described by this fixed point, which is the most symmetric fixed point you can write for a 3-wire junction, you actually have enhancement of tunneling density of states, and you can ascribe it to this negative sign, which is essentially some sort of it's analog of what I said in the case of 2-wire junction, where essentially, so there's something to notice here. For the 2x2 case, you really needed to have something like an Andree process. You really needed mismatch of filling fraction. The interesting point is, once you come to 3-wire junction, the Andree kind of fixed point naturally appear without having any inhomogeneity in the Luttinger parameter. They are there. They are possible fixed points of the theory. So, and if they are there, they give rise to this interesting physics that you really get an enhancement. Now, if you try to summarize, what we see is that, so no such enhancements of tunneling density of states for a 2-edge junction with a uniform filling fraction happens, that we saw. The other thing which we saw is, though a 2-edge junction with non-uniform filling fraction can host an Andree type process, it does not lead to an enhancement of tunneling density of states. So a negative sign in the current splitting matrix is not enough to ensure that you will get an enhancement. So it turns out that the interplay, you need an Andree type process, you also need the right number of channels. If you have both of them right, then you really see an enhancement, which is counterintuitive. You see that something opposite to this orthogonality catastrophe is happening. So that is what makes these junctions quite interesting. And this is something I would like to stress. And the last, okay, I thought it's minus minutes, so I still have 1 minute. So now superconducting junctions. So what is the boundary condition which you impose? So what is a very simple boundary condition if you start thinking about it. All you say is sum of incoming electron current into the junction should be equal to minus of sum of outgoing hole current out of the junction. That's essentially the boundary condition. If you convert that into bosonized language, you will essentially get derivatives of fields here and derivatives of fields here. It will boil down to some condition which will amount to saying that on the current splitting matrix, you have this interesting condition. It doesn't sum up to 1, it sums up to minus 1. Okay? So those are superconducting, they will describe superconducting junction, a perfect superconducting junction, because you're exactly giving out 2 units of electron. So, I mean, are these interesting? Why? So this is one thing which really made me think about it, and this got me interested into it, because recently Anindya has been looking at experiments where really he has graphene sheets in the quantum Hall regime with a junction within a superconductor, and one can look at Andree reflection in these systems. Okay, -1 minute, can I take? Okay. So these are realistic. Essentially, you can think about a quantum Hall edge and a superconductor together, so it's worth revisiting this problem. So this is why we started looking at it again. So what you have here is you can think of a junction which looks like this, where an electron, there's a superconducting boundary condition here, which means that if you have an electron coming in, a simple fixed point would be a perfect fixed point would be, and every electron coming in here bounces off as a perfect hole. So essentially, it's what is called a crossed Andree reflection. That process is perfect. Or you can have situations for a half wire when an electron comes in, a hole bounces off. So again, I'm going to make this comparison of tunneling density of states. So if you look at, so it turns out that there's actually a duality between the normal junction and the superconducting junction, and the duality goes as G going to 1 over G. This is something we showed. So if you look at the bulk tunneling density of states, it is symmetric in G going to 1 over G transformation, so nothing happens. Essentially, it's telling you that even if you put superconducting boundary conditions, you continue to suppress electron tunneling into the wire. So if you try to inject electron here or here, you'll continue to suppress it. But if you have a boundary, which is a half wire, and you try to tunnel an electron here, then for repulsive electron, you really have an enhancement of tunneling density of states. That's really interesting, because it really changes the physics. So you can have an enhancement of tunneling density of states simply induced by superconductivity. You can have other fixed points. I'll just skip this, and I'll come to the last one. So now the last point, so the analog of what I showed you is that for the charge conserving case, there was a fixed point where there was minus signs in the diagonals and plus signs on the off diagonal. Superconducting analog of you can see that if you add up all these rows and columns, they add up to -1. So this is the superconducting analog of most symmetric junction which you can have, where if you send in an electron, 1/3 of the electron comes back, -2/3 holes, and -2/3 hole actually bounce off. So this opposite dip is essentially a hole here. So you have an electron density here which comes in, 1/3 goes back, 2/3 hole goes back, 2/3 hole holds this way. So if you take this guy and you start calculating the tunneling density of state, it turns out you get the same expression, except now actually superconductivity gives rise for the same for the superconducting case, it gives rise to a suppression of tunneling density of states. So initially what I showed you is that if you have a normal junction and you take the most symmetric fixed point, you get an enhancement of tunneling density of states because of Andree kind of process happening. Now we really physically inject somehow superconductivity at the junction, and you write down the right boundary conditions, and then if you look at the most symmetric fixed point, then you get something completely counterintuitive. So it's telling you again, just the Andree processes are not enough, just the number of junction is not enough. It's the interplay of the two which can actually give rise to the situation where you can beat this Luttinger liquid physics that there's an suppression of tunneling density of states. I think with that I'll stop.